Good afternoon, everyone. I hope you're all having a fantastic day. Okay, today is more about related rates. Let's just jump right on into it. I want to try and make this short as possible. Remember a couple of things right off the bat. Your DREADS, which is diagram, rates, equation, derivatives, and then substitute specific info. I got it written down right here for me. Now, remember that one of the common mistakes is to substitute too early. You have to make sure and take the derivative first with respect to t, then substitute. Remember, all of our derivatives are pretty much going to be with respect to t in real life because we're all subject to this little thing called time. So make sure you take your derivative before you substitute specifics. Now, the numbering on these got a little weird, so it says example 2, but this is the one about the dock. It says, at a dock, a winch is reeling in a rope at a rate of 2 feet per second. So we're on a dock, right? We've got a winch reeling in some rope. The winch is 20 feet above the surface of the water, and the rope is attached to a boat. This attachment is at the water's surface. So let's draw a little diagram here. It says, how fast is the boat moving when 22 feet of rope is paid out? So let's draw a little diagram here. We've got a dock like this. We've got some water. Oh, waves. We've got a boat on the waves. Here's my little boat. Right? And I've got a rope going from the winch to my boat. So here's my winch, here's my rope, it's going to my boat, right? And it says, how fast is the boat moving when the rope is 22 feet of rope? So first, DREADS, my diagram. I've got my diagram drawn. Let's go ahead and label some stuff they gave me. It's 20 feet above the surface of the water. Now, do we know what the x value is here, the distance from the dock to the boat? No, we don't, but we know that this is going to be x. And one of the things they're actually asking us is how fast is the boat moving when there's 22 feet of rope paid out? They want to know how fast is the boat moving on x. Okay, but before we get to that, back up here, my rates, I've got a rate of 2 feet per second, but that's rope, right? This is rope. So let's just call it R. That's how much rope we have out. I don't know how much rope I have, so I'm just going to call it R. So the rate at which the rope is changing, dr dt, is 2 feet per second. 2 feet per second. But I have to think about this here. My rope is getting shorter by that amount, right? So I'm going to throw a negative in here. Another little note. Check your negatives. Check negatives. That says check negs. I know it's kind of hard to read, but I'm trying to do this and get all the picture in there as well. So check your negatives. So my rate is negative. My rope is shrinking because I'm wheeling it in. All right, so let's come up with what they're trying to find. Before we do our equation, let's do what they're trying to find. It's asking us to find how fast the boat is moving. Well, that's how fast x is changing, isn't it? How fast is the boat moving? So find dx dt when there's 22 feet of rope is paid out. That means there's 22 feet of rope here. When r equals 22. Okay, so now to the hardest part about this is probably the equation. I've got to come up with some type of relationship between x, 20, and r. I've got to come up with some type of relationship between three sides of a triangle. Now, since this is a dock, this is a right triangle. So I've got to come up with some type of relationship between three sides of a right triangle. Three sides of a right. Epiphany! How about the Pythagorean theorem? We can use that, right? Does a Pythagorean theorem relate three sides of a right triangle? Yeah, sure. So 20 squared plus x squared is going to give you r squared. And that's at any time, right? I can pick any time and I can plug that in there and I can find one of my missing values. So dreads, diagram rates equation, here it is. When you go to find your equation, you are just looking for any relationship that applies to your situation. Any equation will do that applies to this situation. Now in this case, there is only one situation that relates three sides of a triangle, of a right triangle, together, and that's the Pythagorean theorem. Finding the equation is probably the part that takes the most amount of practice. So we're going to go through and we'll do plenty of these. So let's just kind of go along for right now. So after the equation comes the derivative. So I'm going to go ahead and take a derivative here. The derivative of 20 squared is 0 plus the derivative of x squared. Now what are we taking the derivative of? Or what are we taking the derivative with respect to? Remember, this is always the derivative with respect to t in real problems like this. So over time, feet per second, you're changing every second. So I am taking the derivative with respect to t. This is going to be 2x dx dt. And that is going to be equal to 2r dr dt. I took the derivative of x and r with respect to time. This goes back to what we were talking about in class about always being with respect to time here. If you're given a rate that is in time, feet per second, you're taking the number of feet with respect to how many seconds with time. And only after we have done a derivative can we substitute. Now, when you substitute, the idea behind substitution is to get only d over dt left. Meaning I want what I am solving for. In this case, I want dx dt to be the only thing remaining. So I got to come up with values for x and for r. Well, luckily, I can actually do that. For starters here, 0 is just going to go away. It's just 0. So 2, how do I figure out what this x value is, dx dt, when I know that my value for r is supposed to be 22? And dr dt again was given to me right here, -2. So how do I come up with this x when r is 22? Well, I'm just going to go up here and plug it in, do a little Pythagorean theorem to it. How about this? 20 squared plus x squared equals 22 squared. That'll give me x when r is 22, wouldn't it? So let's set this thing up. X squared is 22 squared minus 20 squared. I'm going to plug that in real quick. 22 squared minus 20 squared. And that gave me 84. Forgive that other work that's on there, but 84. So I've got x is going to be the square root of 84. Now I can disregard the negative square root here because I'm dealing with a distance. We can't have a negative distance, so I can disregard the negative for now. But x is going to be the square root of 84. Because again, remember, I want dx dt to be the only variable left. That's the goal. Now I can solve for dx dt. So let's do this. Let's say we divide by 2 just to get rid of some of this clutter. The square root of 84 we can simplify, but I don't need to. So now let's divide by the square root of 84. We have dx dt is equal to, this will be -44, divided by the square root of 84. Now, can you simplify this more? Yes. Do you need to? No. But I would go ahead and convert it to a decimal because, yeah, why not? This is a rate. Decimals are okay. They're acceptable with that. So type in negative 44 divided by the square root of 84. And you get, lo and behold, negative 4.801 if we round to 3 decimal places. Negative 4.801. Now, what is this? What is changing here? dx dt represents what? It represents how fast the boat is moving towards the dock. So this would be a rate then in feet per second. So again, remember what I said about applying this? If we can't apply this to real life, then it doesn't make sense to learn it. So let's apply it to the situation. Write this out here. The boat is being pulled in at a rate of 4.801 feet per second. Now, if you notice in my answer, it's negative, and that's because the distance is getting closer, right? But if I'm pulling my boat in at that rate, then the rate itself can be positive, and that's okay, because logically it makes sense that you're pulling in at a certain rate. Your distance is going to shrink by that same, or by a rate that's related to that. If the rope is getting shorter at 2 feet per second, then your distance is going to get shorter at 4.8 feet per second, at least at this time. That's going to make sense, right? Okay, let's go to the next example. Good question here. This is another one of those calculus classics that everyone loves to ask. An airplane is flying west at 500 feet per second at an altitude of 4,000 feet, and a searchlight on the ground is directly under the path of the plane. It's directly under the path of the plane. That doesn't mean that it's directly under the plane. It's in the path of the plane, right? So basically that means the plane is flying straight at it. If the light is kept on the plane, so you got a searchlight kept on a plane, how fast is the searchlight revolving when the airplane is a distance of, oh, I messed this up a little bit. I didn't type this right. When the airplane is a distance of, I'm sorry, this should be 2,000 feet due east. I'm sorry for the horrible grammar there. Make that little correction, 2,000 feet due east. It should say when the airline is a distance of 2,000 feet due east. So here's what I'm getting at. First, imagine this. Where's my, well, it's a little bit small for that, but you've got a searchlight, right? Say that my pencil is the beam of the searchlight. And for lack of a better description, that's the plane. It's asking how fast is the searchlight revolving. So again, imagine here's my little searchlight, and as the plane flies over this way, my searchlight's going to go pew. It's going to revolve, right? It's going to turn, and it's going to follow my plane. Now I'm moving west, so I'm going to start here and go like this, right? And it wants to know how fast is that searchlight revolving. So let's set this thing up. First, I need to set up my little picture, my diagram. So I've got a little triangle here. Here's my airplane. There's my airplane. And it says it's flying west at 500 feet per second. Uh-oh. That's a direction, isn't it? It's going this direction at 500 feet per second. But what do you know about left directions? We count those as negatives in the real world. Okay, these numbers are getting a little bit big. So I'm going to knock these down, and I'm going to say that here's my searchlight, right? Here's my searchlight, my ball of fire. Okay, I'm going to put this in terms of thousands. What that's going to do is, instead of doing 500, because these numbers are going to get huge if I do this, your plane is flying left, so I'm going to keep that information there. But in terms of thousands, so the plane is 4,000 feet in the air, right? So I'm just going to write this as a 4 to keep my numbers a little bit smaller. I'm just going to understand that it's in terms of 1,000. So this is 4,000, right? We've got our distance changing constantly here. And then it says, if the light is kept on the plane, how fast is the searchlight revolving? What are we measuring here? We're measuring how fast the angle is changing. If your angle is like this, you want to know how fast it's revolving, how fast the angle is changing. We're finding theta. Okay, so I'm going to get a little ahead of myself, so I don't want to do that just yet. I've got my diagram drawn up. I'm going to label the stuff they gave me. They told me that the plane is flying dx dt, the rate of change that it's flying horizontally. Now, since I'm doing this in terms of thousands, let's call that a negative 0.5. And yeah, feet per second. All right, since I'm doing it in terms of thousands, I'm going to call it a negative 0.5. Why not? All right, and they want me to find, think about what they're wanting you to find. They want to know how fast is it revolving. They want to know how fast is theta changing. They want me to find d theta dt when x is 2,000 feet. Or in my case, since I'm counting everything in thousands, when x is 2 feet. And just remember, I'm counting everything in thousands. That's just to make my numbers smaller and more manageable. Okay, so think about this for a second. I need a relationship between an angle, the the height, and the horizontal distance. I need a relationship between an angle, a vertical distance, and a horizontal distance. If this is a right triangle here, which we know it is because it's going to the ground, obviously, I need a relationship between an angle and the opposite and adjacent sides of the angle. Something kind of like tangent of theta. Tangent of theta is equal to opposite over adjacent, 4 over x. Yeah, why not? Let's do this thing. And again, that's going to be the harder part. Remember your dreads. You got your diagram, you've got your rates. Now you need to find an equation. Once you have your equation, the rest is easy. The equation, what relates two legs of a right triangle and one of the angles? In this case, an angle and the opposite and adjacent. Tangent. If I wanted to, I could have done cotangent is x over 4. But that's ridiculous. So after you find your equation, what was the next step? Derivative with respect to time. So let's find a derivative with respect to time here. The derivative of tangent of theta. Now instead of an x or a y, we have a theta, so I'm still going to treat it the same as a variable because we don't know what it is. That's going to be secant squared theta, but since theta is not time, d theta dt. Boom. Is equal to, let's try and rewrite this here. This is the same thing as 4x to the negative 1, right? So just to save us some time, drop your negative 1, you get negative 4x to the negative 2. So how about just negative 4 over x squared? But since we took the derivative of x with respect to time, dx dt. Yahtzee! Okay, this is when things get a little weird. We took our derivative. Everything is with respect to time, so we need to make sure we have our ddt on there. Remember back for substitute specific info, we've only got one step left. Substitute specific info. I want only d over dt left. That means I want only what I'm looking for. I want d theta dt left. It means I got to figure out what secant theta is. So let's figure out what secant theta is. Now, if you'll remember, secant theta is equal to your hypotenuse over your adjacent, right? It's the reciprocal of your x value. X value was x over r, so this is going to be r over x, hypotenuse over adjacent, or, you know what, this doesn't have a variable. Since we're used to calling this radius with your unit circle, let's just go ahead and call this r. So this is going to be r over x, right? That's from the unit circle. Secant is r over x. So we need to come up with r when x is 2. Remember, it was 2,000. I'm just going to call it 2 since we're in thousands. So what I'm going to do here is I'm going to say you have x squared plus 4 squared equals r squared, your good old Pythagorean theorem. And let's come up with r when x is 2. Well, 2 squared is 4, 4 squared is 16, so r squared is 20? Yeah. So r is going to be the square root of 20. R is going to be the square root of 20. So if r is the square root of 20, then r over x is the square root of 20 over x, right? Now, or I'm sorry, on this particular time, instead of x, we have 2. I'm sorry about that. In this particular moment, it's the square root of 20 over 2 because we're doing it a snapshot at this instance. When x is 2, r is the square root of 20. So there's your secant. So I'm going to plug that in here. Square root of 20 over 2 squared for secant squared. D theta dt is what I'm solving for. Negative 4 over my value of 2 squared. Dx dt was negative 0.5. All right. Let's simplify this out here. Negative 4 over 4, well, that's 1. Negative 1 times negative 0.5 is just 0.5. Square root of 20 squared is 20 over 2 squared is 4. Don't forget to distribute your square to the top and bottom. D theta dt. Multiply by 4. Divide by 20. Right? Or you could just multiply by 4 over 20. This is going to end up as 2 over 20, or just 0.1. D theta dt is equal to 0.1. Now that's what we were solving for, right? D theta dt. But what is that measuring? That's measuring how fast this is changing, right? Since we're measuring like this, what's changing here? What in the world is changing? Well, what I'm changing is how many radians this angle is being measured at. Because it would be at a really small radian, and then as the plane got closer, it would kind of turn up like this, and then the radians would keep getting larger and larger and larger. So what I'm measuring here is the number of radians it's changing per second. So again, relate that to the real world. You are changing 0.1 radians per second at the time that you are 2,000 feet away. That's all she wrote, 0.1 radians per second. So d theta says that theta is increasing at 0.1 radians per second when x is 2,000 feet. Now, since that's a ratio, the 0.1 is not going to change because we're measuring angles. 0.1 is not going to change at that time. The 2,000 could go from the 2 to the 2,000. That's okay because you're just measuring a ratio that goes along with this triangle. All right? That's all.